Guys, this is Ishwar, Mechanical Engineering Department. So today we will start model number 2, that is strain rosette. So already model number 1 I have completed one chapter, that is electrical resistance strain gauges. In detail we have discussed electrical resistance gauge. So after completion of model 1, now let us start model number 2. In that, the one important topic, that is strain rosette. Now let us discuss what is strain rosettes. So if we consider a body or a object or a machine member, if you know strain at a point, then we can easily find the other parameters like stress and other things. But if you don't know the strain at a point, you don't know the strain of the direction, so that time what you have to do, you have to orient strain gauges along that. So you will get a strain at a point. So how we can define strain rosettes? The strain rosettes can be defined as the strains are arranged in a systematic way, or the strain configuration we can call as a strain rosette. Strain at a point, if you want to know that point, then you have to orient along that point. If you want to measure strain at x direction, if you want to measure strain at y direction, or if you want to measure inner strain or some other direction also, you have to orient number of strain gauges. Then you have to take that readings, and you have to consider some equations, and you have to find what is the strain at a particular direction and as well as stress at a particular directions. So like this we have to orient, you have to arrange the systematically along any other direction, any direction, so we can call as a strain rosette. In that, the strain rosette is based on assumptions of isotropic and homogeneous. Already you know what is isotropic and homogeneous. Isotropic means, iso means same, tropic means the property same direction. So homogeneous is nothing but the same material in that body, or we can consider the material as same, right? So after that we discuss strain rosette configurations. The commonly used the strain configuration as follows. The first one is 2 gauge rosette, 2 gauge rosette, and the second one is rectangular rosette. In the rectangular rosette also we have another 2 sub division, that is a 3 element and 4 element, and third one is delta or equiangular rosette, and the fourth one is T delta rosette. A better way I will explain by considering that figure. So if you observe that first one is 2 gauge rosette. Okay, the 2 gauge rosette. So one gauge is arranged in a horizontal direction, another one is the vertical direction. So I can say the angle between these two is 90 degree. If you orient like this we can call as a 2 gauge rosette. The second one, in the rectangular gauges we have a 3 gauge rectangular rosettes. So one is placed in a horizontal direction, another one placed in a vertical direction, another one placed in a in between, that is 45 degree. So another one gauge you have to orient, or gauge have to place, that we can call it as a 3 gauge rectangular rosette. So what is the angle of that? One is, I can say that gauge 1 is a horizontal direction, that is I can say that is angle is 0 degree. Gauge 2 is horizontal angle 45 degree, and gauge 3 is 90 degree, right? So another one is huh, 4 gauge rectangular gauges also there. Okay, 4 gauge rectangular. So another one we can orient along 135 degree. So 90 degree and 135 degree. If you orient along another one, just we can consider 4 gauges rectangular rosettes. So next one is T delta rosettes, and you already know that. So T delta, it's look like a, the symbol is delta. So arranged rosette, arranged gauges on this delta rosette. We can say that one is arranged horizontal direction, another one is arranged 3 and 2. Also we have to observe that it is look like a triangle, no, right? It is look like a triangle. I can say that one is 0 degree, another one is 120 degree, the inside is 60 degree, another one is 60 degree. I can say that, right? In this way, if you orient, we can call as a delta rosette. Another one is T delta rosette. Now if you look at that, the T delta rosette, the same similar to the delta rosette. Another one you have to place vertically, that is 90 degree. If you see that, the fourth one is called as a T delta rosette, right? Another one is 4 gauge rectangular rosette. You can observe that. So first, second, third and fourth, they are arranged in a systematic way as well as at a particular angle. One, as I can say, 0 degree, 45 degree and 90 degree, and one is 135 degree. Also you have to orient, right? Okay, another one, or else this one you can also arrange in I can say that the different angle also we have to arrange. It depends upon where exactly we want to measure a strain in a machine member or structural member. Depends upon you. You have to select a number of strain gauges, right? Now, after discussing this types of strain rosette configuration, now let us discuss what is the relationship, stress strain relationship. Already you know the stress strain relationship. So if you consider as a one x and y direction, if you placed 45 degree that, so we have angle, that is phi angle. If you know that phi angle, if you don't know that phi angle, so also we can write in terms of how we can write. We can write you have to observe that. For example, you have a orientation, nothing but you know that degree of that where exactly how placed, right? If you know that, now we can calculate what is the strain at a particular direction, what is the stress at a particular direction. How we can get? Because of by using this available equation. How we can get? So let us take this equation. Epsilon phi is equal to epsilon x cos square phi plus epsilon y sin square phi plus gamma x by sin phi into cos phi. This equations is get given mechanics of material. Already know that. Next, if you know the angle, now we can use this equation. We can calculate what is epsilon x, what epsilon y. Okay, then how we can get the principal strains. Now already you know the principal strain. What is the principal strains and what is principal stress? Already you know that. The strains are acting in x and y direction. There is no strain in other z direction. Then we can call it as a principal strain. The same way the stresses also, if we know the stresses in the x and y direction, there is no stress in the z direction, that we can call it as a principal stresses. So this equation already you have used in I think you have used in DME also, right? Now the principal strains. How we can calculate the principal strain? Epsilon 1 and 2. Okay, you can use 1 by 2 epsilon x plus epsilon y plus or minus 1 by 2 under root epsilon x minus epsilon y square plus gamma x square. So for finding maximum strain, right? By using maximum strain, how we can calculate? You can using this equation, under root epsilon x minus epsilon y square minus gamma x square, right? The principal strain directions also we can calculate by using this equation, tan 2 phi 1 equal to gamma xy divided by epsilon x minus epsilon y. So phi 1 also I can write 1 by 2 tan inverse gamma xy divided by epsilon x minus epsilon y. Like this you can use these available equations, no derivations are required, only just you have to remember these available equations. So derived equations is there, just you have to consider, right? Next, so after discussing this principal strain direction, also we can calculate the principal stresses. Then if you know the strain, then ultimately you will get stress also because of the stress relations. Now how we can calculate the principal stresses? Then becomes sigma 1 equal to E divided by 1 minus mu square epsilon 1 plus mu epsilon 2. So sigma 2 equal to E divided by 1 minus mu square epsilon 2 plus mu into epsilon 1. Using these equations we can calculate the principal stresses as well as principal strains and their directions. Okay, now here also we can look at then two gauge Rosettes. You have one is placed in horizontal direction, that is the strain A, and that is strain B in vertical direction. The angle between these two is 90 degree. I can say that the strain A is 0 degree, strain B is 90 degree. And third rectangular gauge also you have to observe that the strain A, strain B and strain C. Or else I can say that gauge A, gauge B, gauge C. Right? Gauge A is mounted in 0 degree, B is 45 degree and C is 90 degree. Like this you have arranged. Now T delta also, the delta also delta Rosette. So if you look at that, A 0, B and C, right? So B I can say that is angle 120 degree and C is the 60 degree. Like this you have to note. Now another one is the 4 element rectangular gauges. One you have to place 60 degree, one you have to place a 0 degree, another one you have to place a 90 degree, another one place a 120 degree, another one is 60 degree, right? In this way also we can place, no problem. One is 0, 90, another one is 60, another one is 90. Okay, in this way also we can, so according to your requirement you can place any directions, not only for this, not restricted only this one, you can place any other direction. Then the T delta Rosette. See that the same, similar to delta Rosette, another one you have placed in a vertical direction, that is D if you look at that. So this one comes as a T delta Rosette. Okay, now analytical solutions for this one. Analytically how we can derive in a 2 gauge Kirkus delta Rosette. Okay, so these are the important. Now let us discuss. So for that purpose we can consider first one, the 2 gauge Rosette. The 2 gauge Rosette, the Rosette is suitable only the direction of principal strains are known, right? The Rosette is suitable, these 2 gauge Rosette are only suitable, you can suitable only for where the direction of principal strain is known, The gauge A and K is arranged along the maximum strain direction chosen and the x, so that phi A is equal to 0 degree, and gauge B is set only along minimum strain direction, so that phi B is 90 degrees. So one is simply I can say that one is placed in horizontal direction, another one placed in vertical direction. So the gauge A is angle is 0 degree, the gauge B angle is 90 degree. So already we have discussed that if you know the particular angle of placing of that gauges, gauge A, gauge B, using this equation, right, already I have given, using this equation we can determine what is epsilon A, what is epsilon B, because if you observe that in this figure, gauge A, gauge B, I can also write strain A or strain B, right? Strain A, strain B. Now what is a strain A, strain B? Now let us determine. Okay, how we can determine? Using this equation, epsilon phi equal to general equation. You can remember this equation, epsilon phi equal to epsilon x cos square phi plus epsilon y sin square phi plus gamma xy in phi into cos phi. This is general equation you have to remember for remaining analytical solutions method, right? Okay, now I can say that epsilon phi I can write because of you want to very interested to know what is epsilon a. So for that purpose, now first I will take as a right. Okay, now first what you have to do here, this one. Now we are very interested to determine what is epsilon a. For that purpose, so I can write here the equation I will take, the general equation. In that, can I write epsilon a, epsilon x cos square, the phi a, because the gauge a, the angle already you know that. Can I write this one is phi a plus epsilon y sin square phi a plus gamma x plus sin phi into cos phi, because of interested to know that gauge a particular direction, right? Now wherever a is there, no phi a, because of the angle, the phi a angle I already have written as here. If you look at that, the phi a angle, this one phi a angle is 0 degree. Okay, now what you have to do, that 0 degree, now you have to substitute epsilon a as usually you can kept as usually. Now epsilon x cos square phi a 0 degree plus epsilon sin square 0 degree and gamma x plus sin 0 degree and cos a. So now we can simplify this one. You will get epsilon a equal to epsilon. Can we take equation number 1? Okay. Now same similarly epsilon b is having, right? Epsilon b is having angle. Epsilon b is 90 degree. So what we have to do here, this one, epsilon b is 90 degree. Now we will write what is epsilon b. Now come to here. Now epsilon b, now same equation we have taken, wherever epsilon a, phi a is there, no, you can replace by phi b. Okay, so epsilon b, so here phi b, also phi b. So okay, here phi b into cos. Okay, now wherever 0 degree is there, now you can replace by 90 degree because of the phi b is 90 degree. Now if you write or you have substitute that 90 degree, if you simplify this, you will get epsilon b is equal to epsilon y. Now this equation is considered as a equation number 2. So if you know epsilon a and epsilon b, so I can also write epsilon x equal to epsilon a, epsilon y equal to epsilon b. This also we can write, no, there is no problem. Hence already you know that the principal strains epsilon 1 equal to 1 by 2 epsilon x plus epsilon y plus or minus under 1 by 2 under root epsilon x minus epsilon y square, because of there is no shear strain. That's why gamma xy is 0. We have only along x and y direction. There is no shear along xy direction. So that purpose gamma xy is equal to 0. So no need to write the whole complete equation. You can remove that. So I can write epsilon y equal to 1 by 2 epsilon x plus epsilon y plus or minus 1 by 2 under root epsilon x minus epsilon x. So this is also I can write epsilon 1 and 2, right? Now maximum principal strain and minimum principal strain. Okay, now 1 by 2. Now epsilon x also I can write epsilon a plus epsilon y also I can write epsilon b plus or minus under root. So what is epsilon x is nothing but epsilon a minus epsilon y minus epsilon b. So I can replace it by epsilon x epsilon y by epsilon a. So now we can also, you can simplify. If you simplify this, now 2 to get cancelled, you can get epsilon 1 equal to epsilon a. Okay, next. So the same similarly epsilon 2 equal to, you will get epsilon b. Okay, correct? If you take as a plus, you will get epsilon 1 equal to epsilon a. If you take as a negative, that is minus, you will get epsilon 2 equal to epsilon b. Now maximum shear strain how you will get? Already have told that you will take that's under root terms, that is under root epsilon x minus y. Wherever epsilon x epsilon y is there, you can replace by epsilon a minus epsilon b square. So gamma maximum how you can write? Epsilon a minus epsilon b. Now the same, meanwhile you can also write principal stresses sigma 1 e divided by sigma 1 equal to E divided by 1 minus mu square epsilon 1 plus mu into epsilon 2. Okay, already you know that what is epsilon 1 and epsilon 2. So wherever epsilon 1 and epsilon 2 is there now, you can replace by what is that epsilon 1 and epsilon 2. So sigma 1 equal to E divided by 1 minus mu square epsilon A plus mu into epsilon B. So sigma 2 also I can write similarly. Okay, epsilon 2 mu into epsilon 1 is there now. You can epsilon 2 is nothing but epsilon B, epsilon 1 nothing but epsilon A. You can write sigma 2 equal to E divided by 1 minus mu square epsilon B plus mu into epsilon A. So the same way I can also write maximum shear stress. Maximum shear stress I can also write E divided by 2 1 plus mu epsilon A minus epsilon B. Okay, why? Because of we have a general equation tau max, that is the shear maximum shear stress equal to E divided by 2 1 plus mu into epsilon x minus epsilon y equal to tau max equal to E divided by 2 1 minus mu. Wherever x epsilon y is there, you can write epsilon A minus epsilon B. Like this, you have analytically we have derived what is epsilon A and what is B, and how if you know that epsilon A epsilon B, then we can find principal strains epsilon 1 and 2 as well as principal stresses, right? Okay, now similarly if you take as a the rectangular rosette, nothing but in the 3 gauge rosette, 3 element rosette gauge, you have a look at that this figure, you have 3 gauges have oriented along horizontal direction, another on the vertical direction, another one in between that, another one has placed. I can also say that first one in horizontal direction, gauge A, gauge B, gauge C. Okay, similarly I can write epsilon A, epsilon B, epsilon C, right? So this one I can say the epsilon A, epsilon B, epsilon C. So is the x, y, and this one in between that. Now the same similarly I can also write the orientation, that degree. So phi A I can write that gauge A, phi A is 0 degree, correct? It's placed in horizontal direction. Phi B, it is placed in along 45 degree. Phi C, it is also placed in 90 degrees vertical direction. You know that the angle one is 0 degree, 45 degree, 90 degree. Now you have to consider again the same general equation, epsilon phi equal to epsilon x cos square phi plus epsilon y sin square phi plus gamma x by sin phi to cos phi. Now already you have told that wherever phi A and there you can substitute that angle 0 degree, you will get epsilon A equal to epsilon B, and then again you have to substitute 45 degree. Okay, after 45 degree, you can look at that epsilon B equal to epsilon x cos square 45 degree plus epsilon y sin square 45 degree plus gamma x y sin 45 into cos 45. So if you simplify this, you will get epsilon B equal to 1 by 2 epsilon x plus 1 by 2 epsilon y plus 1 by 2 gamma x y. Now again I can also write epsilon B equal to 1 by 2 epsilon x y plus y plus 1 by 2 gamma x y. Okay, now the same similarly if you say that epsilon C is having a 90 degree, if you place wherever the degree is there now, you can place 90 degree, you can substitute 90 degree, you will get epsilon C equal to epsilon y. So solving for equation, solving for epsilon x, epsilon y and gamma x, so we get so epsilon x second at epsilon A, epsilon y equal to epsilon C. Okay, now epsilon b equal to what? 1 by 2 epsilon x plus epsilon y plus 1 by 2 gamma x plus square here. Okay, now okay, now so what you have to do here, 2 you can take this side. Okay, it become 2 epsilon b and epsilon x upon gamma xy. Now because of you want to write gamma xy, because what is shear strain in xy direction, so we are very interested to know what is shear strain in xy direction. So for that purpose I can write here gamma xy equal to, I can write 2 epsilon b minus epsilon x, because again you can gamma xy equal to 2 epsilon b, where epsilon x epsilon y equal to what? Epsilon ix equal to epsilon a, epsilon y equal to nothing but epsilon c. Now replaced. So we have determined what is epsilon x, what is epsilon y, and what is gamma xy. If you know these three, right, then what you have to do, now we have to consider these principal strains. Already you know that epsilon 1 and 2. Now we can substitute what is epsilon x, what is epsilon y, and what is gamma xy. Okay, already you know that general equation epsilon 1 and 2 equal to 1 by 2 epsilon x plus 1 by y plus or minus 1 by 2 under root epsilon x minus epsilon y square minus gamma square. So what you have to do, wherever epsilon x is there, you can replace with epsilon a, epsilon y, right? It is correct. Now if you look at that, okay, epsilon x nothing but epsilon a, epsilon y nothing but epsilon c, epsilon x again a, epsilon y nothing but c. Okay, now gamma xy square, already we have determined this one. Substitute this one, 2 epsilon b minus epsilon c. You will get equation number 5. So you can give equation number systematically 1 and 2 like this. So you can write equation number 5. Now maximum shear strain becomes same if you take under root terms. Under root gamma epsilon x minus epsilon square plus gamma x square. So gamma x equal to under root epsilon a minus epsilon square plus 2 epsilon b minus epsilon a square. Like this it becomes equation number 6. Now the principal strain direction also I can write phi 1. Already this equation also I have given. Just you have to take the general equation phi 1 equal to 1 by 2 tan inverse gamma xy divided by epsilon x minus epsilon y. So in that gamma xy is nothing but already you know that gamma xy nothing but this one, epsilon x nothing but this one, epsilon c, right? So you have substitute, you will get epsilon 1 equal to 1 by 2 tan inverse 2 epsilon b minus epsilon a minus epsilon divided by epsilon minus epsilon c. So phi 2 how will you get? The strain directions equal to 90 degree plus phi 1. So phi 1 is already you know, after calculating will get that becomes, so that equation plus 90 degree will get phi 2. Okay. Now the principal stresses are then obtained from, if you know that principal strain, then ultimately also will get the principal stresses sigma 1. Okay, so what is epsilon 1, epsilon 2, already you know that we can substitute, we will get the equation number 8, e divided by 2 epsilon a plus epsilon c to 1 minus mu plus 1 by 1 plus mu under root epsilon a minus epsilon square plus 2 epsilon b minus epsilon a minus epsilon c. Okay, the whole square, so you will get this equation. Okay, now epsilon 2 sigma 2 also will get, you can substitute, will get same way, the maximum shear stress also will get the same. Similarly you have to substitute that equation or whatever we have determined. Okay, so after discussing the first one and second one, the same similarly the delta Rosette also there. Okay, the delta Rosette, so in that delta Rosette already I have told it's look like a triangle. If you look at it as triangle, it's like a triangle. So one is placed horizontal direction, other one placed 120 degree, other one placed 60 degree. So A, I can say that epsilon A, epsilon B, epsilon C. Okay, now if you look at that, so here I can say A is and B and this one is C. So now this one also I can write epsilon A, epsilon C, and this one is epsilon B, right? So now you want to determine what is epsilon A, epsilon B, epsilon C. So already you know that the angle phi A also I can write phi A equal to 0 degree, phi B equal to 60 degree, phi C equal to 120 degree. The same similarly I can again I will take that general equation and I will substitute 0 degree will get epsilon A equal to epsilon x. Then if you substitute 60 degree, then what you will get? You will get okay, now you can substitute 60 degree. Okay, now 60 degree you can take again you have to substitute 60 degree. Okay, now you can simplify this one. After simplifying this one, you can take that LCM and also you can again simplify. You will get epsilon B equal to 1 by 4 epsilon x plus 3 epsilon y plus root 3 gamma xy like this. Again you have to place you have to substitute 120 degree that equation. Okay, again you can substitute 120 degree, and again take LCM. Again you have to simplify. You can get epsilon c equal to 1 by 4 epsilon x plus 3 epsilon y minus under root 3 into gamma xy. Again consider equation number 2, 3. Add both the equation. If you add equation number 2 and equation 3, okay, ultimately under root 3 gamma xy minus under 3, that both are cancelled. Now you will get epsilon b equal to epsilon c. Again you have to simplify, and you will get this one by 2 epsilon x plus 3 epsilon y. Put epsilon x equal to epsilon. Already you know that what is epsilon. Now you can substitute. Okay, after substituting again you can simplify. You will get epsilon y equal to 1 by 3 2 epsilon b plus 2 epsilon 3 minus epsilon a. So why? Because we want to determine what is epsilon x, what is epsilon b, what is epsilon c. So after that again what is epsilon x, epsilon a, what is epsilon y. So we have got 1 by 3 2 epsilon b plus 2 epsilon 3 minus epsilon a. Now the both equations are subtract. So first what we have done, you have added both the equation, we have got epsilon y. The same similarly, if you have subtract the equation number 2 and 3, you will get this gamma xy equal to 2 by root 3 epsilon b minus epsilon 3. Now what you have to, after getting this epsilon x, epsilon y, gamma xy, now again same similarly what previous I have explained, we can substitute the principal strains equation as well as the direction and as well as the principal stress. We will get these equations. Okay. Now, so after discussing this important analytical solution for 2 gauge, 3 gauge as well as delta Rosette, these are the important, we can go through that. The next session I will take some examples related to 2 gauge and 3 gauge and as well as some delta Rosette. So I will explain in detail how we can determine principal strains as well as their directions as well as the stresses. Okay.